So this is the fourth video on chapter 14, and it's on the different types of the intermolecular attractive forces. And so the strength of the intermolecular forces between the molecules or between the atoms that compose a substance determines the state, the physical state of your substance at room temperature. So it will determine if you have a solid, a liquid, or a gas at room temperature. Strong intermolecular forces tend to result in liquids and solids, so substances with high melting point and high boiling points, because the strong intermolecular force hold the molecules packed together, so that gives a liquid, and if they hold them rigidly in place, then you have a solid. Weak intermolecular forces tend to result in gases, and so that's for substances with low melting point and boiling point. So noble gases, for example, have very weak intermolecular forces between them, and so they are gases, and so the atoms are free to move, free from each other. And so there are four types of intermolecular attractive forces, and we'll focus on those four types in the order from the strongest to the weakest. And so the strongest is the ion dipole attraction, then the hydrogen bonding, the dipole-dipole interactions, and the London dispersion forces. So in order, the strongest is the ion dipole, then the hydrogen bonding, then dipole-dipole, and the weakest will be the London dispersion forces. So we'll start with the ion dipole force. So an ion dipole force exists between an ion and the permanent dipole of a polar covalent molecule or compound. Remember that polar covalent compounds are the only compounds that have an overall dipole, right? A dipole is only for polar molecules. And so what happens is that the partial positive end of the permanent dipole is attracted to the negative ions, and the partial negative end of the permanent dipole is attracted to the positive ions. So in the examples we have here, sodium is a cation, a positive ion, and so it will be surrounded by molecules of water. For example, if sodium chloride is dissolved in water, you will have the water molecule orient their oxygen atom towards sodium, because that's the oxygens that carry the partial negative charge. And then the hydrogens that carry the partial positive charge will orient themselves towards the anions, the chloride ions, if you have NaCl dissolved in water. And so we see this kind of interaction whenever we have a soluble ionic compound that it dissolves in water and becomes solvated. So the water takes away one ion at a time and surrounds it, oriented this way. And you have, spheres of hydration around each ion. And that's how you can dissolve ionic compound. Dipole-dipole force. The dipole-dipole force exists in all polar molecules. So let's note that the ion dipole force can only exist between ions and molecules with a dipole moment. The dipole-dipole force can only exist between molecules that are polar and that have a dipole moment. And polar molecules have a permanent dipole that interacts with the permanent dipoles of neighboring molecules. So they are attracted to each other due to the fact that they have a dipole moment. And so the positive end of one permanent dipole is attracted to the negative end of another. And this attraction is the dipole-dipole force. And so here in the illustration, we have the formaldehyde molecule, and it has a dipole moment. The carbon is partially positively charged. The oxygen is partially negatively charged. And the oxygen of one molecule will be attracted by the carbon of another molecule. And the dipole-dipole force here is represented by the red dashes. Hydrogen bonding. And hydrogen bonding is really a special type of dipole-dipole force. It only occurs for polar molecules that contain hydrogen atoms that are bonded directly to fluorine, oxygen, or nitrogen. And so they will exhibit this additional intermolecular force that we call the hydrogen bond. An hydrogen bond is a sort of a super dipole-dipole force because it's, again, due to the fact that it's dipole moments here, but it's very specific in the fact that it has to be an hydrogen bonded to fluorine, oxygen, or nitrogen. So the different factors are that that leads to this hydrogen bond is that there is a large electronegativity difference between the hydrogen and these electronegative elements, you know, fluorine, oxygen, and nitrogen. And so it's a strong dipole moment. And the small size of the hydrogen and the fluorine and oxygen and nitrogen allows neighboring molecules to get very close to each other. So all of these are small size atoms. So as a result, you have a strong attraction between the hydrogen in each of these molecules and their fluorine, oxygen, or nitrogen on neighboring molecules. So let's look at examples. Hydrogen bonding exists in HF, hydrofluoric acid. In HF, the hydrogen on each molecule is strongly attracted to the fluorine on its neighbor. You can see the red dots here are representing the hydrogen bonding between hydrogen of a molecule and the fluorine of another molecule. Fluorine is extremely electronegative and really attracts the electrons toward itself. The intermolecular attraction of an hydrogen atom to an electronegative element is called a hydrogen bond. So be careful, the name says hydrogen bond, but it's not a chemical bond, like it's not an intramolecular bond that, you know, builds up molecules. It's only an attraction between different molecules, so between molecules, and it's due to partial charges, right? It's not due to, it's not a bond. So be very careful about that. Never draw them as a single line, like the HF bond here. It's really an attraction only, and it's symbolized here by the red dots. Hydrogen bonding exists in methanol, since methanol contains hydrogen directly bonded to oxygen. It's that OH alcohol function. And so methanol molecules form hydrogen bonds with one another. The hydrogen atom on each methanol molecule is attracted to the oxygen atom of its neighbor. And so this way they will orient themselves such that the hydrogen is looking at an oxygen of another molecule that also has an hydrogen bonded to it. So again, here the hydrogen bond is symbolized by the red dots. It's an attraction between molecules. Another example of hydrogen bonding, it's famously occurring in water. The water molecules form strong hydrogen bonds with one another. It's all about HO bonds, right? Water, it's only HO bonds. So everywhere you turn, there is the possibility to do an hydrogen bond between the hydrogens and the oxygens of different molecules. So water molecule form hydrogen bonding, and it really keeps this small molecule because water is really a small molecule, and so it should be a gas, but it's a liquid at room temperature. And there is also hydrogen bonding in DNA. DNA is the molecule that is composed of thousands of repeating units called nucleotides. And each nucleotide contains a base, an adenine, a thymine, a cytosine, or a guanine that are abbreviated A, T, C, and G. And so the order of these bases along the DNA encodes the instructions that specify how proteins are made in each cell of the body. And so DNA consists of two complementary strands wrapped around each other in the now famous double helix. And so each strand is held to the other by hydrogen bonds, and they occur between the bases on each strand. So hydrogen bonds are very important for the molecule of DNA. It gives its double helix structure. And because it's, um, intermolecular attractive forces, they can be broken. And so the two strands will be separated, and that will allow replication of DNA. And replication of DNA can be very specific because the thymine can only hydrogen bond to the adenine, and this way only an adenine will face a thymine. And the cytosine, similarly, only binds to, or, not binds, but is attracted to the guanine by hydrogen bonds. And so, again, only a guanine will face a cytosine. And same thing from the other side. The thymine is the only one that will face an adenine, and the cytosine is the only base that will face a guanine. And so this way, the replication of the DNA is very accurate, thanks to those hydrogen bonds that can only happen between these two complementary bases. So let's look now at the fourth intermolecular force, and that's going to be the London dispersion forces, and it's dependent on what we call instantaneous dipoles. So there are random fluctuations in the electron distribution of an atom or molecule that can cause instantaneous, or what we would say temporary or transient dipoles to form. These transient, constantly appearing and disappearing in response to fluctuations in an electron cloud. So if you look at the figures on the right, frame 1 shows an atom of helium where its two electrons are, around the nucleus, like vertically, one above, one below. In frame 2, time has passed and the electrons have moved, and now one is slightly to the left, the other is slightly to the right. And in frame 3, time has passed again and the two electrons have moved around, and now they are both on the left side of the atom. And so the fact that they are both on the left side of the atom creates an instantaneous dipole that is due to the fact that you have all electrons on one side, so that's going to be creating an partial negative charge to the left, and then the nucleus on the right will create a partial positive charge on the right due to the fact that it's missing electrons on that side. And so an instantaneous dipole on any one atom or molecule can induce an instantaneous dipole on neighboring atoms or molecules, because the neighboring atoms or molecules will feel that partial positive charge or partial negative charge, and that will attract the other electrons or repel them. And so it will induce another instantaneous dipole in a neighboring atom or molecule. And because of that, they will be attracted to each other because of those partial positive charges. Atoms or molecules will, orient themselves depending on that attraction. And so this attraction is called the London dispersion force. The London dispersion force was first recognized by Fritz London, and that's why it has this name. London was born in 1900 and died in 1954. It was a German-American physicist. And so, since all atoms and molecules have electrons, all have an electron cloud, so they will all have the London dispersion forces. It will happen for all molecules or atoms or elements. The magnitude of the dispersion force depends on how easily the electrons in the atom or molecule can polarize, which means can form a dipole moment in response to an instantaneous dipole. So it depends on the size of the electron cloud. So the magnitude of the London dispersion force depends on the size of the electron cloud, and a larger electron cloud results in a greater dispersion force because the electrons are held less tightly by the nucleus, and therefore they can polarize more easily. So a large electron cloud is easier to, uh, move around and adapt to what it feels around it. And so while molar mass alone does not determine the magnitude of the dispersion force, it can be used as a guide when comparing dispersion forces within a family of similar elements or compound. So if you have similar elements of compound and you are asked, which one experiences the stronger force, London dispersion force, then the one with the larger molar mass will have a stronger London dispersion force. So molar mass here refers to the mass of 1 mole of that element or compound. So see it as molecular mass if it's a molecule, or atomic mass if it's an element. And so the larger the mass of the atom, and that suggests the larger the atom and the stronger the London dispersion forces will be. And so we observe that actually with the halogens. It's pretty obvious. Halogens are made of 2 atoms of the same kind bonded together. It's the fluorine, chlorine, bromine, iodine. And because it's 2 atoms of the same kind, there is no polar bonds, right? It's non-polar molecules. Chlorine, Cl2, bromine, Br2, and iodine, I2, are all non-polar molecules. And so they cannot experience, dipole-dipole forces or hydrogen bonding. And so the only intermolecular attractive forces that they experience are the London dispersion forces. And so we observe that chlorine is a gas at room temperature, bromine is a liquid at room temperature, and iodine is a solid at room temperature. How come they are in such different physical states? And so this suggests that the intermolecular attractive forces are stronger in iodine than bromine, and they are stronger in bromine than chlorine. And this is explained by the London dispersion forces, because these are all nonpolar molecules. That's the only force that is in play between molecules of iodines, and between molecules of bromine, and between molecules of chlorine. So the reason why iodine, being the larger atom of the 3, its electron cloud is larger, bigger, so it's more easily uh, it creates more easily instantaneous dipoles, and influences the other atoms around it more easily. And so then you have London dispersion forces in play much more strongly in the I2 than Br2 and Cl2. And again, Br2, bromine is a bigger atoms than chlorine, and so the London dispersion forces are stronger in bromine than chlorine, and so it will be a liquid. And then chlorine, where you will have the weakest London dispersion forces of the 3, so it's then a gas. It's not strong enough to hold them into a liquid phase or solid phase. So you see that even though those London dispersion forces are the weakest of the intermolecular attractive forces, they are still very important and have consequences, as you can see, on the physical state of substances. So let's go through a concept check now, and we will determine all the intermolecular forces in each of the molecules below. And we will select the most important one, and that one will be the strongest force. So I want you to pause the video and work this out on your own before you watch the answer. So HCl is a so it's experiencing the London dispersion forces because all molecules do. So you need to list that always. Then HCl is polar. The electronegativity difference is 0.9 between chlorine and hydrogen. And so that's a polar covalent bond. And so we have a dipole moment, going from hydrogen towards chlorine. And so that means, molecules of HCl will be attracted to other molecules of HCl due to those dipole-dipole interactions. And does HCl experience hydrogen bonding because there is that hydrogen there? Well, no, because for hydrogen bonding to occur, you need hydrogen to be bonded to fluorine, chlorine, or bromine. Fluorine. Sorry, what did I say? Nitrogen, fluorine, or oxygen. Sorry. So there is no hydrogen bonding possible for HCl. It's not bonded to nitrogen, oxygen, or fluorine. HCN. So again, HCN experiences London dispersion forces like all molecules. Now, we saw earlier how HCN is a polar molecule because the CN bond is polar and it's not cancelled by the CH bond because it's a non-polar bond. So we have a polar molecule with a dipole from the carbon towards the nitrogen. And so these dipoles will attract each other, and so you will have dipole-dipole interactions between HCN molecules. Now, does hydrogen make hydrogen bonding in this HCN? No, because again, hydrogen needs to be bonded to nitrogen, oxygen, or fluorine for hydrogen bonding to occur, and it's not the case here. Hydrogen is bonded to carbon. Remember how it is bonded the same way that the formula is written. Hydrogen is bonded to carbon, and it's to carbon that nitrogen is bonded to. And so the dipole-dipole interactions, again, will be the stronger of the two forces here. CH3 and H2. So again, you would list the London dispersion forces. The NH and CN bonds are polar. We can see above here CN bond is polar, and the HN bond is also polar. Electronegativity difference of 0.9. So we have dipole moments that are pointed from the hydrogens towards the nitrogen and from the carbon towards the nitrogen. So they are all pointed towards nitrogen, and so because the nitrogen in this molecule will have a lone pair on the nitrogen, so you will have a shape of a pyramid there, the tripod. Two legs will be the bonds with the hydrogen, and one leg will be the bond with the carbon. And so all these bonds are polar towards nitrogen, and so they add up, and there is an overall dipole oriented towards nitrogen. And so we have dipoles that will be attracted to each other. So molecules of CH3 and H2 will be attracted to each other due to those dipole-dipole interactions. And finally, nitrogen is bonded to hydrogen. And because of that, the hydrogens of one molecule will be attracted to the nitrogens of another molecule. So hydrogen bonding is possible here. And so that's the strongest of the three forces here, hydrogen bonding. C2H2. Again, London dispersion forces need to be listed here. And do we have a dipole there? The CC bonds and the CH bonds are non-polar, so there is no dipoles. So the only force that can exist between C2H2 molecules are London dispersion forces, because The CH bonds are nonpolar, the CC bonds are nonpolar, so there is no dipoles. And hydrogen is not bonded to nitrogen, oxygen, or fluorine, so you cannot have hydrogen bonding either.